Okay, so basically this is supposed to be the 60-story model that you have. And in designing any tall building, you need to decide on the lateral load resisting system, and we decided to be using tube and tube. Frame the tube from the outside, core from the inside. The second thing is that you need to come up with preliminary dimension, and that's the dimension that I gave you. Each group in this project have different dimensions of the columns and the beams. And then you need to prepare the 3D model. And last week I showed you how you prepare the 3D model, either by importing a CAD file and how we, or either using your grids. And once you do it, you replicate the building, and then you draw the out triggers at a specific location and choosing the out triggers dimensions. And then we are going to perform equivalent static lateral load analysis, the one that is here. We need to calculate the base shear and then distribute the base shear forces on the slabs. And maybe we can do responsive spectrum, but maybe we cannot do it. Okay, so let's see how equivalent lateral force procedures according to the ACI 716. So looking at this, the first thing that we need to do is that we need to identify what is the seismic zone that we are working with, because as I told you, designing building in Tennessee is different from Florida, is different from LA. So basically LA or California is a high seismic zone, and usually the ground acceleration is much higher than man. Last semester, I asked the student to use Los Angeles, but actually it was a high seismicity, like the buildings was like making huge drift. So let's assume it's man. So it's gonna be different numbers then. So to draw responsive spectrums in the code, they give you you need to identify a few things. You need to identify the seismic zone, the soil classification, the site coefficient, and then we do two things: risk targeted maximum earthquake and design spectral acceleration. So we don't go all over the things that we have done, but you have to understand where they are coming from, because the codes come up with this procedure from the basics. Okay, so you do the first one is the seismic zone. You will go into the standards here. This is standards, and we're not going to use. I'm going to tell you something else if you don't have the standards. So this is ACI 716. There's another one. It's ACI 722, and then there's a figure. This figure, I believe it's a 12 something, like seismic maps here. And this map tells you what is the seismicity of each state and the location, like a contour map. So for example, here, like Florida, and then you have here California. So you have all the seismic maps here. Okay, so you will be able to get two things. The codes do something. Okay, so this is the responsive spectrum curve that the codes are using. It's similar to the one that I drew here, like it's behind the this projector. It used some parameters to draw it, like, okay, it tells you I'm gonna move linear, and then here constant, and then go with parabolic curve and another parabolic curve. Each one of these has equations. It depends on parameters. What are they? SD1 and T. And here you have SD1, TL, and T squared. So these parameters is coming from the basics that we are talking about. And it gives you what the equations that each one is using. Like this one, use this equation. Like if your structure have a fundamental period from 0 to T0, so you will have to use this function to get the acceleration. If your structure have a fundamental period from this to this, you will have to use this one. If your structure have a period from here to here, you'll have to use this equation. Okay, so this is the responsive spectrums that the codes are using. Okay, so let's get back on how to determine these parameters. So basically, I go into the maps and get two values. One of them is called the SS, which is the short period acceleration, and one of them is called S1, which is the 1 second acceleration. I get these two, and then I use what is called soil classification. This soil classification gives you two parameters to multiply these by two numbers. It's called FA and FV. Like this, two parameters. And you modify these two numbers by the soil. Because if you have an earthquake hitting a ground, if one on a rocky soil is different from the one on a stiff soil. So based on the soil, these numbers is gonna be big or is gonna be high. So we modify them based on the soil, and then we will end up with two new values. One of them is it's called SMS and SM1. So if you look back there, it was S and 1, right now we have M, which stands for risk targeted maximum considered earthquake. Then if we want to go for design, the design reduces this earthquake by 33%. So it multiplies this number by 2/3 and 2/3, and you come up with a new acceleration. So basically, we want to calculate two acceleration. One of them is for short period building, which is the first one. One of them is for long period building, which is this one. If we knew these two, we will be able to draw the response spectrum curve. This one, if we knew this too, because it's this one and this one, okay? So basically it's a procedure. You go into some figures, grab some numbers, modify them by the soil, and once you do them, you will be able to draw this curve. However, there are some tools online that can help you to escape all of this. How? If, for example, if you go to Google and search for USGS design ground motion, and you go here, you design ground motions US, and then you will find the tool is called ACI 7 hazard tool. And basically you will look for your location. For example, I will put Miami, Florida, and you will search, you check seismic, this box, but you will have to tell the tool what is the risk category. Okay, so there is something, it's called risk category. So for example, if a building is a hospital, so it will be a high risk category. If a building is a residential building, it's different category. So based on the category, the base shear is gonna be multiplied by a factor to increase the base shear. For example, if we have a hospital, maybe the risk category is gonna be 1.5. So the base shear, rather than being, for example, 1,000 ton, is gonna be 1,500 ton. Why? Because this is a high risk category facility. We need to design them for a much higher earthquake. But for our example, we have risk category 2. If you want to know what is the risk category is, you go in the standards. Maybe you will search, for example, risk category. What is it called? ASSE 722. So for example, here's the definition of the risk categories. Let me zoom in. So for example, it says occupancy of the buildings or structures. Okay, it says buildings and other structures that represent low risk to human life in the event of a failure. It's risk category 1. For example, risk category 3, buildings and other structures, the failure of which could pose a substantial risk on human life. Then it tells you, I believe, here, the buildings that has hazardous fuel, chemicals, and I believe hospitals are somewhere down there. But for our building, it's risk category 2 because it doesn't exist in all of these categories. So all buildings and other structures except those listed in risk category 1, 2, 3, and 5 or whatever, or 4. So it's risk category 2. So, and then there's another table that tells you based on the risk category,
Like actually, I have this table here. Tells you based on the risk category,
this is the definition of each category. Okay, and based on each category, it tells you what is the importance factor that you should use. For example, risk category 1 and 2, if we are working with seismic, so the importance factor is 1. So if we have a base shear 1,000 tons, we multiply by 1, so it stays the same. But if we, for example, if we have a hospital, so it's gonna be a risk category 4, so it's gonna be 1.5. Okay, same thing happen actually with the snow load, ice load. Each one of them has different important factors. Okay.
right? So let's get back to this tool. So it's risk category 2. The second thing it asks you for, what is the soil type? For our project, we are going to assume a stiff soil, soil type D. Stiff soil, okay? So it asks you for these two parameters. Why it asks for the soil? Because it wants to do the same procedure that I told you about a few minutes ago. It has the maps already, so all what he needs is the soil so that he can calculate the site coefficients, FA and FV, and then do the other procedure. Once it's done, you will view the results, and then you can actually show details, and actually it will show you the responsive spectrum for your area, how it looks like, but this is I'm not interested into right now, and it gives you a summary.
This is the important thing that we need for our project. So it gives you what the SS before the soil coefficient and after you add the soil, and gives you the design spectral acceleration of your building, S design, these two parameters. And it gives you what is the TL, which is the long period. Like if we have a site, like for example, Florida, Los Angeles, Tennessee, or any building, each one has a long period of your structure. So it has a parameter like this. TL is equal to 8. We take these parameters and put it in ETABS as is.
So let's see how we can do it in ETABS. So let me get this one. Okay, so this is the structure that we built last week, the 60-story model. We have the outriggers, we have everything, and it's ready to take the seismic load. But before putting the seismic load, you need to make sure that all the other load patterns are defined. So the dead load, the live load. Let me delete this one so that we can do it together now. Okay. Define load cases. Let me delete the I want to make sure that the slab has loads. Okay, yeah. So for this model, we are going to use so we will have the loads for the project. I believe I put this in the project description. We are going to have the on weight of the structure. And number 2, we are going to have flooring. We are going to have live loads and earthquake. Okay, so this is the loads that we have. On weight, the structure is going to calculate it for you. If you put the self-weight modifier equal to 1. Flooring, you have to assign it by yourself, and the value of the flooring is going to be 150 kilogram per meter square or 0.15 ton per meter square. Okay, so this one thing The live load is gonna be 200 kilogram, which is 0.2 ton per meter square. You need to assign it in your slabs. The earthquake, we are gonna use equivalent to staticness. And I will show it to you right now. So assigning any one of these loads, for example, I have the 60-story and I didn't assign any load. So basically, I will select all the slab, for example, select properties, slab 30 centimeter. So I select, see here, 60 shell elements. And right now I can assign shell loads, uniform, and I'm gonna choose live load. I'm gonna put 0.2 ton per meter square. I'm gonna say okay. So if I right click on this slab, for example, like this, so it has a dead load 0.15. What is the dead load 0.15? It's the flooring load that I put. So where is the on weight? The on weight is already there, but you cannot show it because it's embedded in the self weight modifier. But this one is an assigned load by the user, which is, so 0.15, 0.2. And and then we will say, okay. All right, so I put all the loads. Let's see how we can put seismic load. But before putting seismic load, I need to remind you a few things. Okay, so we need to do, let me write these notes because this is very important. Because this is kind of like software thing. We need to do it. Remember, number one, the things to do your model before you run it or before you do any seismic load. You need to do stiffness reduction. Number two, you need to assign diaphragm, and I'm gonna tell you what is this. You need to define mass source. Number four, you need to adjust the mesh size. What are these? The stiffness reduction is the thing that we talked about a few minutes ago, that since we are using reduced loads, so we need to reduce the stiffness. You'll tell me, how can I reduce the stiffness? So basically, ACI Code, which is the American standard for concrete design, it has a table here, and it tells you the effective moment of inertia for the columns need to be 0.7 of the gross inertia. The walls, if it's a cracked, it's gonna be 0.35. It's uncracked, it's gonna be 0.7. We are not gonna go in this debate between cracked and uncracked. Actually, designers what do? They run the model with uncracked section, and then they check if the section got cracked or not. If it's cracked, they're gonna adjust the model and adjust the inertia of the walls. But we are gonna assume uncracked section. So columns and walls are gonna have a stiffness modifier of 0.7. So we are gonna reduce the stiffness by 30%. Beams is gonna be 0.35, slabs is gonna be 0.25. How can I do this? So you will go to your ETABS model and select all the columns. Select, property, frame section, and you will go to the column 100 by 100 and select. So it select around almost a 7,000 column. And how can I change the stiffness? You are gonna assign frame, and there's something is called property modifier. Property modifier is ask you, right now I have the stiffnesses of all these columns working by 100%. In terms of cross-section area, shear stiffness, torsional stiffness, moment of inertia. So what we are gonna do, we are gonna adjust the moment of inertia about x2 and x3. So if the earthquake is coming from x, so it will find that the inertia is not working 100%, same thing with y.
So this is gonna be 0.7 and 0.7.
And the torsion as well. So let's see also the torsion. So just in case if there's any torsion on the building. So 0.7, 0.7, and 0.7. And then okay. So right now I decrease the stiffness of the columns. The second thing, you will do the same thing with the walls. Like for example, you will go select, and then you will select properties, walls, and we will select the walls and the outriggers. Okay. And then you decrease the stiffness. Same thing with the slabs. And you will use the parameters in this table. Okay. You can get back to the recording and know what is the stiffness reduction factor. Let's assume that we have done that. And let's get back here. So the first thing is done, the stiffness. The second one, assigning diaphragm. So if you didn't assign diaphragm, your model is going to be run forever. Why? So what we do is in lateral load analysis, we doesn't care about the building like bending, like I mean like the slab bending, like what is the slab is gonna happen in what is gonna happen to the slab in the floor. We only need from the slab its weight as a mass and how much is gonna be pushed away from the building and making straining action on the column. So we tell ETABS, don't do any analysis in the plane or don't care much about how the slab is gonna bend in plane. Assume this slab as a rigid diaphragm and adjust the moving X and moving Y. Because I'm doing lateral load analysis. I'm not caring right now about the bending or the gravity analysis of the slab. So you select all the slab in your models. For example, let me unselect everything. And here you will go select, properties, slab section, and you will select the slab 30 centimeter. So right now I have selected 60 ones, and you will go to assign shell, and in shell you will find something is called diaphragm. This one, D1. And you can modify this diaphragm. So diaphragms, there's some of them are flexible and some of them are rigid. Depends on the openings in the diaphragms, the slab thickness and everything. In our project, we are gonna assume rigid diaphragm. Rigid diaphragms is something that is very rigid and it's taking all the columns together, like all the columns in the shear wall. If this is not a diaphragm, so that means that the slab is getting extended in X and Y, okay? So this is the second thing, the diaphragm, and once you are done, you will say, okay, diaphragm is very, very important. If you didn't assign diaphragm, your model will keep running forever because it will do lots of analysis inside the slab, and this takes lots of time. The third thing, the mass source. The mass source is, did you guys remember when we talked about the effective weight for lateral analysis? Mass source is going to tell you, you're going to tell the ETABS what is the effective weight of your structure. So you go to ETABS here, and you go to define. You will find something is called mass source here. And when you go to mass source, you will find one is defined. You can define as many as you can, but I'm gonna modify this one. And right now, ETABS is using only the dead load as a mass source. So it's only coming from the self weight and the additional masses, this one. But if we want a partial contribution from the live load, you need to make a specific load pattern. But the thing is, I have something more than the dead loads because I have flooring. So I need to make a load pattern, and I have dead multiplied by 1. Okay. And the flooring actually is in dead load. So actually I can unselect that. If you have flooring in a separate load pattern, it's called flooring, you'll have to add flooring multiplied by 1. But what I did here, I assigned the flooring inside the dead load. So dead load has flooring and has on weight. So basically I can unselect this. And then I will say, okay, so right now I'm done with the mass source. So right now the effective weight is coming from the dead load. The mesh size, when we do lateral analysis, do you guys remember what mesh size that we used all over the project that we have? The homeworks, 0.5. When we do lateral analysis, we don't care about the mesh size to be that small because we don't care about the bending moment. We care about only the mass of the
the slab. So we make the mesh size much bigger so that the analysis can run faster. So right now I use the mesh size of 3 meters. It's very, very big. It's not gonna give you an accurate moment. I don't care about the moment right now. I only care about the slab mass and how it's gonna absorb force from the earthquake. So we decrease the mesh size so that we can make the model run faster. I would recommend to use a mesh size equal to the size of the spacing between columns. Because if you have columns spacing 2 meters and you use 3 meters, that means the columns is not gonna be connected. Okay, so 2 meters. If you have 2 meters spacing between the columns, you use mesh size 2 meters. How can I adjust this? You will go here to analyze, and then you will find something is called automatic mesh setting for floors. And rather than make a general mesh, you will say rectangular mesh and adjust the size to be 3 meters rather than 0.5 meters. Okay, so that's all for today. And next time I'm gonna go in details in this ETABS model, how we can extract results, how we can show results, what are things that you want to show in your project, and it will be the last lecture related to the project. Okay, so these 4 things are very, very important before running a model for an earthquake. So take care about these 4 things. Okay, see you guys next time.